Hi everyone, and welcome to our first full week of school. This opening slide has one of my go-to activities. I like to see if you can identify and correct mistakes. This tells me that you understand the topic by looking at and analyzing someone else's work. A student simplifies an expression as shown below. Find the error or errors and simplify correctly if need be. So you're going to look at this problem step by step. It's an order of operations which we had just worked on in one of our last sessions. So take a few minutes, copy the problem into your notebook the way you see it, and then look at it step by step and see if you can find where this student may have made one or more errors. When you find them, either circle them or identify them in words, which is something I like to see. The student made an error in step 1. They should have done this and they did that. So give me a little narrative as well, and then find the correct answer. I'm not going to go over this on the video, but we will discuss it in our Zoom lesson today. So our third section, which is lesson 1-3, real numbers and the number line, is going to give us the foundation of what types of numbers we're looking at. We're going to be able to classify them, graph them, compare them, and then we're also going to be finding and estimating square roots, both perfect square roots and some that are not. Real numbers. See if you can make a list of all the subsets. Well, what's a subset? A set is a collection, and generally we put a collection in these notation here. And if you could either write it in notation form or just give the words of as many subsets of real numbers you can think of. And again, we will be discussing all of your options because I'm going to touch upon a few and you may come up with a few more that's not on my initial list. And for a good reason, because I'm focusing on certain types, but we will be talking about all of them. So feel free to add as many as you can on your list. So when I think of real numbers, I'm going to be focusing on the rational, the integer, the whole, and the natural. Now I have a list below here that I'm not sharing with you right now because I'd like to hear some of your suggestions before I share what else is on mine. Now rational numbers are numbers that are can be written as a ratio or in fraction form, and as decimals they're either terminating or repeating. Integers we know to be positive and negative whole numbers, including 0. So if I wanted to write that in set notation, I would have negative infinity, and maybe -2, -1, 0, 1, 2, and positive infinity. Whole numbers. Whole numbers are the set that starts with 0, 1, 2, 3 into positive infinity. And our counting numbers, or our natural numbers, start with 1, 2, 3, 4, ... Okay? Now, rational numbers, all those include those fractions, include some terminating or repeating decimals. And there we have some of the subsets. The only one I didn't mention in the set of real numbers are my irrational numbers, and I'm coming back to that. So real numbers, rational and irrational, whole numbers, counting numbers, integers, can all be represented on a number line. We can graph or plot them by using solid circles to show their place on the number line. I have 4 different numbers: square root of 25, -3/2, 2 5/10, and -3. If I were to graph these on the number line, well, the square root of 25, now that is a radical, and some radicals are rational and some are irrational. This happens to be a rational radical because I can simplify this to be just 5. So 5 can be represented here as C. Negative 3 halves. Now again, that's an improper fraction and it's negative. So that's going to be a negative 1 1/2, which is D. 2 5/10 falls halfway between 2 and 3 on the positive side, and negative 3 down here at A. Now that I've graphed them, I can use these numbers or their corresponding letters to compare them. I could say that D is greater than A. I could say that B is less than C. And you see that I can use this now not only to number them from least to greatest, if I wanted to order them, so now I can compare them, but I could also use this to order from least to greatest, which is ascending order. Go back and I'll say that the least of these is negative 3, followed by a negative 3 halves, followed by 2 5/10, and lastly the square root of 25. So this number line is good for graphing, for helping us to compare, as well as ordering from least to greatest. Now, the second part of our lesson after classifying is to talk about square root expressions. Now, the square root of an integer is a perfect square root. I could have the square root of 36. That's going to be 6. I have the square root of 100. It's equal to 10. But when the radicand, which is the number underneath, is not a perfect square root, we have two options, and one is just to simplify. Now, if I said the square root of 16 is 4, and the square root of 25 equals 5, well, the square root of 17 falls right somewhere in between here. If I were to take my calculator and put the square root of 17 in, I would get a never-ending decimal, and that decimal would be that number would be somewhere between 4 and 5. So again, looking at this helps me to estimate the value. Okay, so let's just take a look at, this would just be a decimal going into infinity. Square root of 102 falls somewhere between the square root of 100 and the square root of 121. Well, this is equal to 10. This is equal to 11. This will be approximately equal to 10 point something. Okay, it's greater than square root of 100, less than that. Okay, falls in between. Now, sometimes another way to simplify would be, instead of estimating, would be to look for perfect square root factors. Now, you may have done this before. There's another method where you just put it into its prime factorization. I like you to get used to this method where you look for perfect square factors. So I know that square root of 25, or 25 times 2, would give me 50. So I could have the square root of 25 times the square root of 2, which becomes a whole number 5 times radical 2. This is something that takes a little bit of practice. We're going to think about how we can find perfect square root factors. So we want to get comfortable with those perfect square roots. And one of those things that we'll do to do that would be to make the list. And that is something that we will do. Okay. So now if I look at the next one, I could think of numbers that give me 40. Well, I have 4 times 10. Well, square root of 4 times the square root of 10 would give me 2 square root of 10. Now 10 can be broken down to 2 and 5, but neither one is a perfect square root. Let's try a couple of more of these. Square root of 700, not a perfect square root, but I do know that 7 times 100 gives me 700, which gives me broken down into 10 square root of 7. Now looking at the combinations of 12, I could look at 2 and 6 or 3 and 4, but I'm going to choose 3 times 4 simply because 4 is a perfect square root. 48. After practice, you will know that this is 16 times 3, which is going to give me 4 radical 3. I generally start using some of the same numbers over and over again so that you become comfortable with them and they become sort of second nature to you. See if you can try these next couple after seeing my few examples. Trying to break them down into factors, and hopefully you can find one that is a perfect square root. In this first one, I'm going to choose 9 times 6. Yes, it's 2 times 27, but that's not going to help me with this process. I'm going to get 3 square root of 6. The perfect square root gets simplified and becomes a whole number on the outside. What remains on the inside, the radicand, stays inside. Now in our next in-class session, I'm going to do this with a little bit more details so that you can see exactly how this works. I'll go into this definition, I'll go into our perfect square roots, but until then, you'll get an opportunity to practice just a little. Thanks for your time today.